Okay, well, thank you again for inviting me. And my most difficult decision was to put me in the program, but I was convinced myself uh, after 2 minutes. Okay, I'm going to talk a little bit about flavonoids improving health, evidence, and potential mechanisms, and I think it's going to fit a little bit with what's said in the two previous talks. I think I will try to go in 20 minutes in all this stuff, and then I want to start saying that we live longer, but that still we don't know if we are living better. It seems that we are living worse, and you can see here how diabetes is darker, is more incidence of diabetes or prevalence of diabetes, and how we expect the world is going to become darker, more diabetic in the coming years. We see here an article from The Economist that about half of the population eat too little, too unhealthy, or too much. Then half of the people is not eating well, and that is how relate nutrition with health. Essentially, we are more interested in unhealthy nutrition. But the good message came several years ago when a paper by William Willett said that most of these risk factors and diseases can be prevented by changes in the diet. And well, then it's good is that we are living longer, we are getting more ill, but still we can do something for our health. And that is something that was pointed by Fulvio before, and I think we change a little bit how nutrition are related with health, because for many years nutrition was talk about deficiency and how the deficiency leads to a disease. But today we try to prevent and we try to advance promoting health and increase life quality. And that is a major change, because many times we are a little bit blind in that direction, because we need to prevent something that we are not sure that is going to happen. Then we have to really trust in epidemiology and very limited clinical studies. We are almost convinced, especially Argentinian people, that we eat a lot of beef, that the fruit and vegetables are good for our health. And we need, but it doesn't mean much. And I mean, because at the end, we start having some questions. The first one is any fruit and vegetable is equivalent? Then if the obvious answer is no, they are not equivalent. And then the next point is, how can we identify from a scientific, from a chemical point of view, why an apple is better than a potato? And then we need to identify why they are better in terms of health, and then we need to go to substances, we need to go to this called phytonutrients, and then to try to also not only identify, but also to be able to quantify, to say why one apple could be better than the one of all the apples are going to do the same. Essentially, if we think that they are just carrying the bioactive species, okay, anyone can have a different value. And finally, we need to identify the mechanisms responsible for the health effects. I think in other ways, we talk about polyphenols like it's a big amount of compounds that are completely different in terms of their activity, inclusive coming from the same plants. And then we need to know the mechanism, we need to know, to understand how we can improve the consumption, if we need to improve the consumption or not. And here, because it's where we mostly are in terms of trying to identify the mechanisms. We believe that flavonols, going to just to try to narrow down the amount of polyphenols that are available and are present in the plant. We know that we try to just to study what happened with flavonols, and at least to postulate that some of them are responsible for the health effects observed by fruit and vegetables. Okay, I'm going to show now some evidences that point out that these flavonols can be responsible for the health effects. And you see here just a meta-analysis of several studies in which were studied different cardiometabolic disorders, all of them, heart failure, strokes, and you see that after the consumption of chocolate, but not chocolate only as a candy, but as a carrier of cocoa and cocoa products, I think these cocoa products were able to improve or to reduce the risk factors in most of the studies that were meta-analyzed here. And the same happened in other meta-analysis in which only was taking blood pressure. I'm going to come back to blood pressure later, but again, there is a good amount of the studies that can be put in this site, reducing the risk factor associated with hypertension. And another disease that is diabetes, and we have also the different studies show a protective effect of consumption of flavonol-rich cocoa on the HOMA-IR scores. Then this is a good indicator that these compounds are doing something for our health. In this study that also mixed it a little bit with mathematics, but it's a model, and they could just make an identification of one product among these or within these studies that were also included the cocoa studies, and they identify epicatechin as the molecule that was related to the observed effect, and with an amount of 20 milligrams of epicatechin per day led to significant reduction of 4 millimeters of mercury in these studies. Then epicatechin seems to be the molecule that could be some of the effects that are observed in fruit and vegetables, and we were really interested in that. What is epicatechin or catechin? Are a molecules of flavonols, are compounds like this. And I want to mention something here that is why I'm showing this molecule. We want to see, when we talk about many years, we say, okay, these are antioxidants and they have antioxidant effect because they're trapping radicals or they are chelating metals, and then we just focus in this part of the structure. But I think, anyone knows, as it was mentioned before by Fulvio, this molecule has different possibility of action, have multiple reaction centers, and just to fix in one reaction center is just totally arbitrary. Then they could be an antioxidant, and we will discuss a little bit that later, but also they can do some other chemical reaction that could be more associated to the in vivo action. Another point to consider is what are the concentration and how is the bioactivity of these compounds in the body. And I think when we take a flavonoid-rich food, the concentration of these compounds are going to be probably millimolar. We take a couple of glasses of wine, it's going to be millimolar in the gastrointestinal tract. But then when we go to the intracellular milieu, then the amount of these compounds are going to be very, very small, and probably it's going to be less than micromolar, or how we can express that. And when we go, for example, to blood, I think we take about this 20 milligrams of epicatechin in the form of the food. I think still we will have less than or very low micromolar concentration in our blood, and it's going to be last only 2 hours. Then it's going to be reduced very sharply. Then the concentrations are something to consider when we talk about total flavonoid, but also when we talk about the metabolites, we know that they are metabolized very fast, and many of these compounds are really fastly metabolized, and then inclusive they can be ruptured by the colonic microflora and then reabsorbed, and then they can have a concentration of compounds that were completely different than what we would take in our food. Then this is saying something about that at the different levels, at the different compounds could be making different action in the biological system. Then the matrix is very, very complicated. Well, we just try to fix in this part of the total flavonoids and trying to see just this rough concentration that most of them are reached, but it's a normal food. Then what are the mechanisms that we can think of backing the effect of these polyphenols? And one was free radical scavenging and metal collection, antioxidant action. And they have chemical structure that easily justify a free radical reaction, and just they can become a compound that is normally well stabilized, then reducing the rate of generation of radicals. Also can chelate metal, taking metal like iron out of the game, and then just preventing oxidation. However, we need high concentration, and we, for example, made a comparison of how a lipid peroxide is going to react with different components of plasma. Okay, the relative rates that you arrive are very different. Then that means that, for example, epicatechin that can reach some concentration of 0.3 micromolar after the consumption of a flavonoid-rich food or epicatechin-rich food is going to be about 25 times slower to react with a peroxyl radical that it is vitamin C or tocopherol, if we just forget a little bit about lipophilicity. But again, I think it's going to talk about resveratrol, it's going to be about 5,000 times less reactive. Then again, as was pointed before by Fulvio, I think these compounds probably are not going to be able to be a physiological relevant antioxidant in terms of trapping radicals. But when you treat animals, and for example in the gastrointestinal tract, we just published results. I want to show that when you treat animals, you see a reduction of parameter of oxidative stress. And then something is going on there that is making an antioxidant action, but it's not by trapping radical. It could be another mechanism. It could essentially, in the long term, could be the stimulation of the antioxidant defenses. But also, we observe, and it was something that go in line with what Valerie was saying before, that there are some membrane effects. Also, this compound could interact with membranes, and they are changing the characteristic and the function of these membranes. And that is going to, for example, here, this is example with intestinal cells, just hexamer, that is 5 units of epicatechin, they are able to reduce the oxidation induced by just a chemical oxidant, but also are able to reduce the oxidation induced by TNF-alpha that is just needs to be bound to the membrane to be active. And then a compound that doesn't go into the cell is able to have an antioxidant action, reducing the increase produced by TNF-alpha as at the same level N-acetylcysteine or lipoic acid, and these are antioxidants that normally go into the cells. But by outside, by membrane interaction, they are doing some effects. Here is the same, just preventing pro-inflammatory and pro-oncogenic signals. That is the activation of ERK and AKT. And that is done by outside the cells, just generating an effect inside the cell that is really started or is not able to be, it shouldn't be related to the incorporation of these compounds into the cells. Finally, in terms of what could be happening with these compounds at the membrane level, we study how this compound could interact with lipid raft, and we observe that they can have an effect on lipid raft. And you see here, this is an inhibitor, and you have the incorporation of a lipid that is very characteristic of the lipid raft. And when you incubate with hexamer, it's practically this compound doesn't go into the cells. Then, in certain way, that is correlated with the reduction of the activation phosphorylation of RK, and the RK that is produced by the hexamer. Then, in certain way, the hexamer is stabilizing the membrane by interacting with the lipid raft and just allowing this membrane to have the normal function in terms of the activation of intracellular signals. And that is just an abstract. What happens is the stress and how flavonoid can interact by outside the cells, also by just modifying some part of the cell, and also in some moment, if they are able to go into the cell, they can be a normal antioxidant or just a regulator of cell signaling. But they also can interact with specific proteins, and that is another important mechanism that was just pointed out many years ago by Helmut Zies. And as you see, apocynin and a metabolite of epicatechin, they have a very similar moiety that could be inhibiting the action of NADPH oxidase, and this could be another mechanism. The important thing about this is that it can be this interaction with membrane of protein can have an effect at concentration significantly lower that can have that you need to have a radical trapping effect. And this is another study that we did in terms of interaction with proteins. And this is the protein of this is a model of the protein of NF-kappa B. You see the unit P50, and you have hydroxyl group, and we have a dimer that is a B dimer that has this. The modeling has this hook structure, and when you have the B dimer, it has an inhibition of the NF-kappa B activation. But when the dimer is the other kind of dimers that they don't have this hook, and they cannot allow the hydroxyl group to interact with the hydroxyl group of the P50 proteins, they cannot inhibit either the NF-kappa B activation or the product of this NF-kappa B activation measured as for example, as a cytokine increases. Then you need to have, and that is the case that you don't have only the 3 and 4 prime position in the bare ring, but you need other hydroxyl group and different position to have this action at the protein levels. Well, that is essentially the same. Well, you can see here that what is the reason is that this dimer of epicatechin is very similar to the one in pair, and this protein has a consensus DNA that needs 2 or 3 G bases, and that is very characteristic to these NF-kappa B proteins. Then you need to have, and what they are doing, we are not inventing nothing. It's just making something that in the nature and how the proteins are designed, and how we can mimic this design, and how a dimer of epicatechin could be doing some of these effects. Again, this is another example how epicatechin could prevent inflammation and insulin resistance. And again, this is a TNF-alpha mediated effect that you need the receptor in the membrane, then you need an interaction with the protein, and in this case, again, the epicatechin is preventing the union with the structure. Finally, I want to show some experiments in rats about coming back to hypertension, and we observe we give epicatechin to rats. You have and also inhibitor of nitric oxide synthase. You have an increase in blood pressure, and we give epicatechin to the rats. That is the black, the white circles. You don't see these effects. This was dose dependent, and here when we take out the epicatechin for the diet, there's a normal increase in the blood pressure. Then epicatechin was preventing this increase in blood pressure that was associated with a prevention of oxidative stress, and essentially with no changes in the expression of nitric oxide synthase, but yes, with the diminution of the L-name increase in super NADPH oxidase effect. Again, as mentioned before, it's an effect that we believe is related to NADPH oxidase activation. This is another model. This is a spontaneous hypertensive rat, but essentially the results are very similar. And we want to what I want to point out is that we think that this relationship between nitric oxide and superoxide is dictating the way the bioavailability of nitric oxide, what is going to maintain the normal vascular function. We have an increase in oxidation just by an increase in NADPH oxidase activity or proteins or assembling or superoxide production. You have a decrease in nitric oxide, and that could be related to increase in superoxide. Conclusions: flavonoids and flavonols are molecules with several reaction centers and consequently can exert different molecular actions. And I normally don't like to say polyphenols or flavonoids are good for your health or whatever. We need to talk about molecules, and in terms of health effect, flavonoid intake seems to affect vascular function and certain oncogenic processes, essentially mostly associated with the intestinal health. However, the mechanisms ascribed of this effect should be consistent with the local presence of flavonoids and their metabolites. We cannot just think in an effect and just say, okay, we forget totally how much compound we have there. Finally, flavonoid health protective mechanisms could be in part explained by the capacity to these flavonoids to modulate redox, inflammatory, and oncogenic signals. Again, perhaps they are doing some antioxidant effect, but it's not as we used to think that it's just an totally unspecific free radical scavenging action. I want to thank essentially all these people that have been working in the last years in our lab, and the co-responsible for many of these studies is Patricia Oteiza, and also have some collaboration with other people at the University of Buenos Aires. And of course, I want to invite all of you. That came the commercial part of my presentation. And we have 2 meetings in October, one after the other. You only need to go to one place and have 2 meetings. That is one to the price of one. And that's going to be in Buenos Aires from October 14 to October 19. And that is a school of law. And we do that because we say we are free radicals. Always people complain about being free radical, and then we do in the law school just in case don't be taken to the jail. And also have some really nice picture of Buenos Aires and also of Argentina that many of you already know, but everybody's welcome. Thank you very much.